This presentation will demonstrate an instance when arrays and pointers cannot be used interchangeably in C. In C, array references can always be rewritten as pointer references. Since C does not provide any facilities for the programmer to pass arrays to functions, arrays are always passed as pointers. Additionally, the compiler always converts the array subscripting operator to pointer arithmetic followed by a dereference. This means that in most cases, arrays may as well be pointers since they are turned into pointers. However, always following this assumption can lead to some confusing errors. This presentation shows an instance where the compiler does not treat arrays and pointers as the same. To start off, we need to know about objects in the context of C. Roughly speaking, an object is any piece of data in a C program. This could be a function or a variable. You probably have not heard about objects in C before because this is a concept related to the linker. But the important thing to understand about objects is that they can only be defined in one place, but can be declared in multiple places. The definition can only happen once because that is when the compiler allocates memory for that object. However, declarations tell the compiler that an object already exists somewhere else, so you can have declarations in multiple files and a definition in one file. Don't confuse object definitions and declarations with variable declarations and initializations or function prototypes and definitions. Say we have two variables x and y. We assume that they have been declared. Since that is the case, the compiler recognizes them as defined objects. As the compiler has allocated memory for these variables, it can also hard-code their addresses relative to the stack. The stack is a segment of memory allocated to the program by the operating system. There is a subtle distinction between the address of x and the contents of address x. For example, if we assign y to x, they are interpreted differently by the compiler even though they are both variables. The compiler interprets x as the address that x represents. Remember that the compiler can hard-code this address in the assembly code it emits. However, for y, the compiler interprets it as the contents that y represents. We cannot go directly from the address of y, something the compiler can hard-code, to the contents of y. This is because the contents of y can change when the program is running. Where y is located, however, cannot change. This means the compiler needs to emit an extra assembly instruction to fetch the content of y. We will now examine how referencing arrays works under the hood. In this case, the variable a is an array of 3 characters. If it has been initialized, it has been declared, and so we know the compiler can hard-code its address. Let us give it an address of 100. During runtime, we first retrieve the index from the subscripting operator. It adds this index 1 to 100 to get 101. We then retrieve the character from address 101, which returns B. If we reference pointers, the steps are different. In this case, A has been declared, so the compiler can hard-code its address. Let that address be 100. During runtime, we first retrieve the contents from address 100. Let us say that content is 200. We then interpret the 200 as an address and retrieve the character from address 200. What if we define a variable as a pointer and then reference it as an array? In this case, A has been initialized, so the compiler can hard-code its address. Let the address of A be 100. Since A is a pointer, the first step is to retrieve the content from address 100. Let that content be 200. Now we retrieve the index from the subscripting operator, which is 1, and we add it to 200 to get 201. Then we retrieve the character from address 201. This yields us B. Note how this approach yields the same result as if we declared A as an array instead of a pointer to a character. However, this approach requires an extra instruction. This is why array references can always be rewritten as pointer references. You can make simpler instructions more complicated, but not the other way around. We now finally examine a case where arrays and pointers are not interchangeable. In C, it is possible to have a global variable shared across multiple files. If we follow the rules for objects, we know that global variables must have a definition in one file, but can have multiple declarations across other files. This does not matter what data type the variable is. Let us say we have a shared global variable named shared. It is an array of 3 characters. In the declarations in other files, do we declare shared as an array of 3 characters or as a pointer to a character? If we thought that arrays and pointers are the same, then both these approaches should work, but in practice, only one approach works. We can only declare shared as an array of 3 characters. In truth, we don't even need to tell the compiler that there are 3 characters. The only thing the compiler needs to know is that it is an array of characters. Remember that declarations don't allocate memory, and the 3 is used in conjunction with the data type to tell the compiler how much memory to allocate. Before we go over what instructions the compiler will generate, let us remember that since shared has been defined, the compiler can hardcode its address. Let that address be 100. If we try and declare shared as a pointer to a character and then retrieve the second character from the array, the compiler will emit instructions to do the following. First, retrieve the contents from shared, which it thinks is a pointer. This yields the character A, which has an ASCII value of 95. Next, add the array subscripting index 1 to 95, which yields 96. Then retrieve the character at address 96. Notice how we treated a character as an address. This is not what we wanted to happen. At this point, we would hope that the operating system has terminated our program because we tried to access memory we shouldn't have access to. The alternative is worse because we don't know what the memory at address 96 is used by, and if the program keeps on running, really bad things could happen. If we instead declared shared as an array of characters, the compiler will emit instructions to do the following. First, add the array subscripting index 1 to 100, which is the hard-coded address of shared. This yields 101. Then retrieve the character located at address 101, which yields B, and this is the expected value. In conclusion, defining as an array and then referencing it as a pointer can lead to unexpected results. I hope you learned something new today. If you're still here, then you might want to stick around for a bit of a more in-depth look. On the left, we have some simple C code. We declare a string in 2 different ways and use the same array subscripting syntax to access the second character B. On the right, we see the x86-64 assembly generated by GCC. You may want to refer back to this slide. The parts of the assembly output we care about are the 3 instructions for accessing S1 and the 2 instructions for accessing S2. The extra move instruction for accessing S1 is because we need to first retrieve the address held by pointer S1. The contents of this address is the address to first character of the string ABC. If you are wondering about the usage of the AL register, it's because a character is only 8 bits wide.